Okay, so we have been discussing about the CPU and memory bottleneck, and we also uh, discussed that the main memory latency is usually much higher than the processor cycle time. Now, if we look at the trend in or the trend in which the processor speed has improved with over the years, and if we look at how the DRAM performance have improved, you will see that there is a stark difference. So I'm showing this plot from the book Hennessy Peterson, and you see here that the processor and DRAM latency gap, and it's a normalized plot. So basically over the years we see that the processor has exponentially gained in terms of performance. So processor speed has exponentially improved after around 2000. That growth rate has tapered a bit, but still it is a very good growth rate for processor. Whereas if you look at the way the memory has become faster and faster, that uh, that is that is not very encouraging. So there is a huge performance gap between processor and memory, and that is why if you just take a simple example, if you have a processor which is accessing uh, a DRAM, uh, by the time, so if you take a typical processor, let's say 2 gigahertz, operating at 2 gigahertz, um, and if it is accessing a DRAM which has a delay of 100 nanosecond, the processor can by the time the by the data is available from DRAM, but the processor can actually perform 800 different instructions. So you see that the processor is much more capable, but the memory from where the processor needs to get the data is not that fast. There are different reasons. I'll try to highlight some of them. So one reason is basically you have if you want to make the memory really dense, and in that process you want to minimize the number of transistors, and if you minimize the number of transistors, your speed goes down because of the way you design your processor. So DRAMs, as I mentioned in the previous discussion, that it requires only one transistor. So in terms of density it is very good, but in terms of speed it suffers a lot. So the key point to, or key takeaway from this is that there is a huge gap between the processor and memory performance. So we want to achieve higher and higher performance or higher computing capabilities, but since we have a stored program model, the bottleneck becomes the memory, because you have to get the data from memory to work on it and then store the data back into memory. Even if you can do this function very quickly, the processor is capable of doing it, let's say 100 times faster. Then let's say your memory access takes 100 nanosecond, whereas the processor can um, uh, execute the instruction in 1 nanosecond. So after executing that instruction, the processor will have to wait for 100 nanosecond more to get the new data, and then only it can work on that new instruction or new data. So even if my processor is capable of doing things much faster, but this, if I can't solve, or this is not improving its performance, then I will not be able to achieve my desired performance. So this is the main problem which we should be aware of in terms of processor memory performance gap. All right. Now there are some other physical limitation. So physical limitation in the form of how big your memory is. So let's look at it. So let's take one example that I have a processor. So let's say this is my processor, and then my memory is, let's say, relatively small in size. So I have a small memory associated with the processor. Now because it is a small memory, the physical layout of that memory, if you look at the diamonogram of that chip, you will see that it is taking, maybe just for sake of one example can be, let's say it takes a area of 1 millimeter by 1 millimeter, and this is your processor. All right. Now since this is 1 millimeter by 1 millimeter, all the wires interconnecting the transistor, because you remember that this memory is implemented using transistors, and the transistors are interconnected by wires. Now these wires, now with technology, let's say we move from one technology to another. So 22 nanometer to, let's say, 14 nanometer, then 11 nanometer, now we are talking about 5 nanometer. So as we move from different technology nodes, um, our transistors become faster and faster. So if I had a transistor in 22 nanometer, and if I today have a transistor in 5 nanometer, the switching speed of my 5 nanometer transistor will be much higher compared to the 22 nanometer transistor. But transistor is only part of the story. I need also wires to interconnect those transistors. Now those wires will have their finite delays, they will have their capacitance. Basically you can model the wires as basically a combination of resistor and capacitor. So that can be a simple model. So if I have, let's say, 10 millimeter long wire, I can model it with its equivalent resistance and capacitance to calculate the delay offered by that wire and all these things. Now if you have a basically, if you want to really model that wire, and if you want to capture all the effects of wire, then you have to model it as a transmission gate. So basically you have to also include inductance, but let's not go there, and we will keep it simple, and we say that okay, the wire is modeled by a resistor and a capacitor, and it will have finite delay. Now if the wire is longer, then the equivalent resistance and capacitance will be more, and that will result in a longer delay. So this RC is proportional to the time delay that this wire offers, and if I have longer wire, then the delay will be longer. So even if I have very fast transistors, so let's say I moved from 22 nanometer to 5 nanometer today, and I can really run my transistors very fast, but the wires which are basically interconnecting these transistors, they will create a bottleneck. Now if you have a small memory, then this length of those wires will be smaller. So you will not the performance will not get affected much. But think about it, a situation where you have your processor here, okay, and then you have a huge memory, okay, because there are basically need for large memory. And if you get a chance, just Google diamonogram pictures of maybe latest processors, etc., and you will see that almost a huge, or most of the part of the chip is only memory. So if this is your whole chip, maybe 70-80% of the whole chip is memory only. So you are reserving most of your chip area for memory. So your memory will be big. Now if you have a big memory, Obviously, the interconnect which are connecting these different let us say elements in the columns will be long, alright. So, you will have long wires. So, long wires will result in longer delay or more delay. Apart from that, if you have big memory, the decoder, so basically there will be some circuitry which will be activating the particular row, particular column whenever you need to read them. Now, if you have a big memory, those circuitry will be connected to many such rows and columns. Now, there is a concept, I am sure all of you are familiar with the term called fan out. Now, let us say I have a simple gate, just think about a inverter. Okay. Now, if this inverter is, now how I will calculate the delay of that inverter? So, the delay of that inverter will vary depending on what this inverter is driving. For example, if it is driving, let us say one another inverter of same size, same characteristics, then it will have a delay. If I use this inverter to drive, let us say instead of one inverter, I use it for driving 4 inverters, the delay will be more, because now this at the output of this inverter, the amount of capacitance it will be seeing is much more. So, basically again, if you increase your capacitance, your delay, because of the RC factor, the delay will increase. So, this phenomenon is called fan out. So, how many similar gates this inverter is driving, that number is called fan out. So, in this case it is a fan out of 4. So, basically you are driving 4 identical inverters using this inverter, and that is why it is called fan out of 4. Now, this delay is a standard delay, and if you increase your fan out from 4 to let us say 8, the delay will increase, and so on. So, now as you make your processor memory bigger and bigger, the decoders, the circuits which will be activating different row and columns, they will be connected to more and more such row and columns, and that is why their delay will become more. So, one thing is basically you will have longer wires, and because of that your delay will improve, delay will be more, and the other thing is the fan out will be more, and that is why you will have again longer delay. So, if you make a big memory, so the speed of that memory will go down. Okay. So, if you need faster memory, the memory has to be small, and if you want big memory, the memory will be slow, because of the physical limitations or the physics involved in the way you have built this memory. All right. So, the takeaway point is that because of this physical observation, physical limitations, if you have big memory, the signals has to travel further, and that results in longer delay. So, I will just write it here. So, signals need to basically travel further, so it will result in longer delay, and on the other hand basically the fan out fan out will be more. So, since you are fan out to more locations, so your delay will be more. So, because of these two primary reasons, if you have a big memory, you will not be able to achieve very high speed. So, performance of memory, so you have to take a trade off. You want to really fast memory, go for a small memory. If you want big memory, it will not be fast. Now, this is a very critical thing which need to be dealt with. because you want your all the data, all your instruction, you should be able to store in your memory. So for that you need to have a memory which is big enough. But on the other hand, if I have a big memory, my speed will suffer. And as I have already mentioned, that if you look at a chip, you will see that most of the chip area is covered by memory. So at one end we are saying that we will not be able to achieve high speed if we have big memory, but on the other hand we are seeing that for storing all our data and all our instructions properly, we need big memory. And if you look at the applications like CNN, DNN, or other similar algorithms, which are basically depending on lot of data. So you need, and they will be working on lot of data, so you need huge amount of data, and for that you need bigger and bigger memory, because you can say that okay, I can make the memory hierarchical, but still if you want to go from one hierarchy to another hierarchy, there is a lot of penalty. So you can't just make memory hierarchical and assume that um, things will work perfect. So you need memory, big memory, and you need them to work fast. So because of the physical limitation, big memory can't work fast, so we have to find out some alternative ways to achieve that. And one of the most interesting alternative way to achieve this performance is memory hierarchy. So basically you break down this whole big memory into at least several parts, and gradually the memory which is closest to the processor, you try to make it really small and very fast, and as you move further from the processor, your memory will be big, but it will also be slow. Okay. So let's now look at memory hierarchy. Okay. So what do we mean by memory hierarchy? So remember that we are trying to solve this problem, that we want memory which is fast, but we can't also live with very small memory. We know that if I make my memory really small, I will be having a fast memory, but I can't live with very small memory. So I need something to compensate for that. So this is my processor, all right, and this is my big slow memory. All right. So basically this is generally implemented in DRAM. Now what we are saying is that okay, this is there. So now you add additional memory here, which is a small and fast memory, and it can be implemented using register files or SRAM, and this sits in between your big slow memory and your processor. So see, we have already partially discussed this when we were motivating ourselves why register files are needed. So we said that okay, since the processor will take longer to get the data from big slow memory, can we put some registers in the CPU itself, which the processor will be directly using, and you will be loading data from main memory to those register files. Now we are just extending that idea. We are saying that okay, register files are still limited. Can I even have a fast and small memory more closer to the processor, which is whose access time is not as fast as register file, but it can be accessed much faster compared to the big slow memory. Now here, just like while we were talking about register files, that there are limited number of register files, so you have to first load your operands in the register files, and then you can use them for your execution. Here also you have to somehow make sure that the data you are looking for should be there in this small fast memory, because even if I have this small fast memory, if the processor needs a data which is not here, then you have to anyway get it from the big slow memory, which will introduce lot of penalty. All right. So to make it work, you have to have some mechanism so that the processor, the data the processor needs is most of the time available in this small fast memory. If that is not the case, then you will not be gaining much, because you have to most of the time get the data from your big slow memory. All right. So we already have seen this, but I'll just reiterate quickly that in terms of capacity, so you have resistors which will have very little capacity, then you have SRAM, and then you have DRAM which has the highest capacity. All right. In terms of latency, so resistors are the fastest, then you have SRAM, and finally DRAM. Okay. And of course, like if you can put this thing in the chip itself, in the CPU itself, then you do not have to go off chip to access the data, and that improves your performance significantly. Whenever you need to go off chip to access some data, the delay suffers very much, because of the pins which you use to go outside the chip. Actually they have huge amount of capacitance, inductance, and that results, and that introduces lot of delay. Okay. So in case of data access by the processor, if the data is there in this memory, then basically you can access the data with a very low latency, and from SRAM. And if the data which the processor is requesting for is not available here, then you have to wait for a long latency, long access latency of DRAM. Okay. So the key point here to remember is that the memory hierarchy will only work if this small fast memory actually stores data that is reused by the processor. Because if every time you are getting new data, then and it is not getting reused, then it will not be very useful, because you have to get the data from main memory every time, and that is as good as directly talking to the main memory instead of this intermediate stage. So I'll just write it down. So memory hierarchy is only work if the small fast memory actually stores data that is used by the processor. So basically memory hierarchy will only work if the small and fast memory actually stores data that is used by the processor. Now is there a valid let's say reason, or is there any evidence that we can effectively use this small fast memory? This can be only done if there is uh, some patterns or predictable ways of uh, memory usage. So if the processor uses memory from in a particular pattern, then we can predict and we can prefetch those data and make use of it. But if there is no pattern as such, then it will be if the data is, let's say, randomly accessed from memory, then it will be very difficult or almost impossible to make use of this small fast memory. Okay. So fortunately, uh, if you look at the access pattern or memory reference pattern, there is very significant there is a lot of interesting things to observe. So generally, if you have written your code in memory, um, basically as a set of instructions, so you will see that the instructions are generally written one after another. So if so, this is in the x axis we have time and y axis we have address. So let's say at time almost equal to 0, this memory gets accessed where your code is written or instructions are written. Now in the next clock cycle, you will move to the PC plus 4, then PC plus 4 and so on, okay, till you hit any loop or anything. Okay, if there is a loop, then you will do this in a again very systematic and iterative manner. So this is one way of one pattern of memory access. So this is instruction fetches, and instructions are very regular, so we can pretty pretty well predict that what is the next instruction that is going to be accessed by just looking at this kind of pattern. So we can come up with some formulation, and this is called uh, this is called basically spatial locality, because here you are accessing a particular memory, and you are uh, and if you access that particular memory, it's very likely that you will access something which is nearby as well, and that's why when you fetch this data, you ensure that you fetch some extra data also, and obviously those extra data will have this memory locations. All right, so this is called spatial locality, and we see in our lot of our programs, etc. Spatial locality is a very common phenomena, so you can exploit that spatial locality. Similarly, you can look at other kind of access like stack access. So you will be maybe whenever there is a call, subroutine call, you will be pushing things. So push, do some work, and then you start popping up, and so on. All right. So this is this is a combination of let's say spatial locality, and then this is temporal locality, because temporal locality says that if a location is referenced, it is very likely to be referenced again in the near future. So here you see that the same location has been referenced multiple times. So this is an example of temporal locality. And then there are data access patterns. So data generally are stored in arrays, so you will read one element after another and so on. So you can also see very regular patterns in the access of data in the processor. So basically you you see spatial and temporal locality very prominently there. So if this spatial and temporal locality is already there, then we can try to exploit that spatial and temporal locality. Just to give you some practical result which are generated from a real machine. So basically this is time, just like the previous slide, and one dot per access to the address at that time. So basically every dot represents an access, memory access, and at different times. And this is taken from the uh, from from this source. All right. Okay. Now if you look at these dots, you see that there are different locations where there is spatial locality. So basically this looks like some instruction access pattern. There is some temporal locality, same data being accessed multiple times, and then there is a combination of spatial and temporal locality where both spatial locality and temporal localities are exploited. Okay. So we do see that there is a pattern which can be exploited if we want to build hierarchical memory hierarchy. Okay. I hope this makes sense. So this is where we now start discussing about caches. So cache is nothing but this small fast memory. Okay. And we would exploit both temporal and spatial locality. So basically it exploits both type of locality. Okay. Now how do you exploit both spatial and temporal locality? So we exploit the temporal locality by remembering the contents of the recently accessed location. So for temporal locality, we do not uh, get rid of the data which has been recently used. We try to keep it for little longer. And for exploiting spatial locality, so what we do, if we need to, let's say, fetch block 3 from main memory, so instead of only fetching block 3, we try to fetch block 1 and 2 as well, 1, 2 and 4 as well maybe. So in that way we can exploit the spatial locality by fetching blocks of data which is data around the recently accessed location, and these blocks are called cache blocks. Okay, so just to put it down, so exploit temporal locality. By remembering the contents of recently accessed locations. The other thing is spatial locality. So these are very important, and these are the building blocks for understanding of cache. by fetching blocks of data around recently accessed location. Okay, so basically fetching these blocks of data, so this is also called cache block. Okay, now let's look at what is there inside the cache. Okay, so we are now going to look into inside a cache. So this model remains. So we have your processor, and then we have our cache, and then main memory. So we have communication between cache and main memory. We have communication between processor and cache. So basically processor sends an address for some data, and data is provided by cache. Similarly, processor can also ask to update some data. So the data is both ways, and the address goes in this way only. Similarly, in the from the main memory we have address. Basically cache sends the address and it gets the data. Similarly, cache also updates main memory. Alright, so this is what the cache from top looks like. Now what is there in this cache? So if we just expand this, what is there inside it? So we have basically blocks of data. Okay, so let's say, and this each row is a data block, and each row is also called cache line. So cache line is this complete row. Now what all are there in this row? So then first thing will be basically address tags. So if this is 100, and then there will be uh, bytes where data are stored. So basically these are all data bytes. So on. All right, now let's say we want to know what is this data which is stored in this cache line. So in this cache line, the data stored is basically a copy of main memory location 100. So this is nothing but your address tag. Okay, so this is your address tag, and this means copy of main memory location 100. So whatever is there in the main memory, you are keeping a copy in the cache, and you are keeping the same address, and then you can basically there are different bytes, so you can address those different bytes, or the different bytes will have their own location. For example, this data byte will be in the location 101, and this is the data byte which is stored in the location 100. Okay, and and these different data bytes actually are called blocks, data blocks. So we'll have different bytes, okay, and all this uh, part is called data block. Okay, so this is how the cache looks like. So it keeps a copy of the data in main memory, and it has the same address. You can find out the exact data by this offsets byte address. So basically each byte will have their own address, and that's how you can read the values in the cache. Okay, so we will revisit this when we talk about how to determine whether the data is available in cache or not. Now if we look at the basic cache algorithm for a, let's say, load operation, so let's look at this basic cache algorithm for a load. So the way it works is basically first processor issues load request, to cache. Okay, then what the cache will do, it compares the request address to the cache tag and sees whether there is a match. Request address, and see if there is a match. Okay, now if the answer is yes, then you basically return the data from cache. Okay, so basically return the copy of the data from cache. Okay, now if that is not the case, so this is for cache hit. So whenever the data is available in cache, we call it cache hit, means basically found in cache. Okay, now if there is a cache miss, um, so that means not in cache. Then you read block of data from main memory. Okay. Now this data which you are reading from main memory, it has to be now mm, uh, stored in the cache. Now cache will have already some data, so you have to replace some cache block to accommodate this new data block. And so for that you need to have a replacement policy, and we will talk about this replacement policy in our subsequent discussions. So basically let's assume that the replacement policy is there, and with that replacement policy we found out which block need to be replaced, and that's where the new block will be placed. So replace victim block. So the one which will be evicted is called victim. So replace victim block in cache with new block. Okay, and then you basically return the copy of data from cache. Now because of the way of implementation, some of these things can be done parallelly also. That's why even if it looks so reading the block from main memory is the most time consuming thing, and once that is done, these two things can be done parallelly, so it will not be so the dominant part of the power consumption will come delay will come from here. Okay. Now before we do anything else, we need to basically understand what are the different types of caches. So we will next discuss about the classification of caches, and that will start in our next discussion. All right.